Alright guys, hey, welcome to the
Can we zoom in, please?
Heckling down to like a zero? I'm looking at you guys.
Full screen.
full screen.
Slide.
Okay. Alright, welcome to the Trees and Graphs talk. My name is Felipe Fernandez and I'll be doing this presentation. So before we begin, is there any new faces in the crowd? Like this is your first time here and never been here before? Okay, cool. Hey, can you stand up and introduce yourself?
Hi everybody, my name is Mauricio Flores and it's my first time here. Welcome.
Alright, what's a little bit about your background? Or you don't have to, but
I'm not in the field, but I'm interested in the field. So I found you guys on Meetup, so I figured why not start here.
cool. Hey, fantastic. Let's give him. Hey, thank you for being here. All right, cool. I hope you enjoy the talk. All right, so we're gonna talk about trees and graphs. Trees and graphs is a topic that you'll come across in certain interviews. Usually the ones that are more like the bigger companies. So it's good to know this, to review it, and to have a good understanding of it. So before we begin, I just want to keep this at a beginner level, and I'm not going to go too deep because trees and graphs is a very broad subject. So what I'm going to do is I'm going to focus on what you usually see in the interviews, because that's what we want. We want to get like interview skills, so we want to be ready for the interview. So I'm not going to go too deep. I'm going to keep it at a beginner level. All right, so it's good to know recursion. So raise your hand if you know recursion, if you're familiar with recursion.
I know.
All right.
Recursion.
Recursion? All right, looks like Tony knows. So, hey, Tony, so if you were to define recursion, how would you define it?
Would it be like a function that calls itself?
Exactly. So, excellent job, Tony. Supportive here. So, as Tony said, it's a function that calls itself to accomplish a task. So, yeah, it's good to know this when you're doing trees and graphs, especially when you're recursing through them. All right, so object-oriented programming. So, who's familiar with object-oriented programming? No one's gonna raise their hand. I got Luis in the back. So, how would you define object-oriented programming?
That's a very good question.
That's a very good question.
Well, I see an example would be like C#, where you have objects that are oriented.
Yeah, pretty much. Yeah. So exactly. So yeah. So you can think of it as the paradigm in which objects contain what's called methods and properties. Methods being the functions within the object, and properties being the variables within the object, and you use those to call and accomplish certain tasks. So, and basic data structures. So we had a lot of talks about basic data structures, including stacks, queues, and linked lists. So most of you are familiar with those from our previous talk. So it's good to know this when you're going into trees and graphs, because it's a bit more advanced. There's more to it, and it relies on existing data structures to create these trees and graphs. All right. So what is a tree? So who is familiar with trees and graphs? Anyone a little bit? Kind of? Okay, cool. So a tree is a data structure, and it's a data structure composed of nodes. So you may be asking, what's a node? So a node in this context is an object with a value, and perhaps like it points to other nodes. All right, so each tree has one root node. So in a little while, I'll draw you what a tree is. And a root node has 0 or more child nodes, and trees are not cyclical. And examples of trees that we use in the real world are the DOM structure and folder structures, right? So, all right, so you could think of a tree as something like this. Right? So this is a basic tree. So a tree can even be composed of one root node. It just has one node. So can you guys tell me, is this a tree? Can someone, April, continue?
I mean, I'm thinking yes.
So in this case, it's not a tree because it's cyclical. Cyclical means that it would go around in a circle.
I was gonna say that line at the bottom is the only thing that's making me think of that.
Yeah. So how about something like this? Is this a tree?
Yes.
Yeah. Why is it a tree?
This is a tree with no branches.
It's a tree with no branches, right? It's just a stump. It's a root. Right, cool. Any questions about what a tree is? Cool. Fantastic. So now there's different types of trees. There are a lot of types of trees. And some examples of these tree-like data structures are ABL and red and black trees, which are self-balancing trees. These are two self-balancing trees. Self-balancing trees are trees that when there's different types of self-balancing trees, but if there's more nodes on one side, an example of it is when there's more nodes on one side, it will get those nodes and put it on the other side. So it could be complete. Complete's not the right word, but because there's full, complete, and then there's some other type, but just think of it as self-balancing. There's heaps. Two heaps are min heap and max heap. Min heap has the lowest value on the top as its root. Max heap has the largest value as its root. There's tries, which is used in when you're searching for something. Is usually used for words to calculate the word branches. We're not gonna go over any of these because they're like more advanced. I want to keep it basic. So another type of tree is a binary tree and a ternary tree, and there's some other trees that are defined by the number of nodes that they have. So a binary has how many nodes max?
Dos.
2. Cool. And ternary has 10, right?
Yeah.
So then there's ternary trees. There's other types of trees, right? So I want to focus on binary trees. So a binary tree is a tree with a max of 2 nodes, right? So if it has 1 node, it could be a binary tree too. If it has 0 nodes, it could still be a binary tree. Okay, so then there's a binary tree, and then there's a binary search tree. So a binary search tree is a binary tree where the left nodes are less than or equal to the root node, and all the right nodes are greater than the root node. Certain types of BST trees don't allow for duplicate values, meaning that binary search trees that don't have duplicate values all have unique values, whereas some binary search trees could have like a value of 2 in one of its nodes, and then on another branch it could have another value of 2. And in interviews, be sure to ask for clarification. So you could ask, oh, what type of, they might tell you, oh, build a binary tree. And you could ask, what type of tree? Is it a binary tree, or do you want me to build a binary search tree? And then they'll clarify. So it's very important to ask your interviewer questions whenever you're dealing with trees and graphs. So I'm gonna draw real quick the difference between a binary tree and a binary search tree. So this is a binary tree. 2 nodes, right? Is this a binary search tree? Let's ask someone in the crowd. I see David over there on his computer.
Yes.
What's the answer?
Yes. Why is it a binary search tree?
Why?
Because the left side is less than the right side.
Cool. 1 is less than 2, right?
Yes.
3 is more than 2, right? Congrats. So if we have something like this, what type of tree is this? Is this a binary search tree? No, this guy's shaking his. No, why?
Because 4 is greater than 3.
Okay,
Something
cool.
like
Good answer. All right.
But technically, just because you're drawing that to the left, that doesn't mean that has to go to the left.
Yes, that's right. So it doesn't have to go to the left. For this context though, you're gonna see a lot of times where it goes to the left. So is this a binary search tree or is it a binary tree?
Yes.
Yes. Yes to both, right?
Yeah.
Good job, man. All right. Cool. next topic is, or next section is binary tree traversals. So then there's three traversals that you should know. There's in order, pre-order, and post-order. In order, you look at the left node, then the root node, then the right node. Pre-order is you look at the root node, then the left, then the right, and then post-order you do right node left. So begin with the board. I'm gonna give you guys examples of what that is. So let's say we have a tree that is wet. Hey, how's it going? Okay. So in order would be left node right. So does everyone know what a traversal is, what it means?
Mm-hmm. Wait, what?
Raise your hand if you know. Okay. Traversal is a term to like navigate. So when you think of tree traversals, you're navigating through the tree. So in this case, we're using an in-order traversal. We're traversing in order. And I'll show you why it's called in order, right? For binary search trees. So we look at here, right? This root node. So where do we look at first? The left, right? So what's at the left? 1, right? So we're right here. Where do we look? Where do we look next?
Back at the node?
Back at left. So is there any children here?
No.
So there's nothing, right? Then we look at the node, right? So what's the node? It's 1, right?
Okay.
So in this case, I'm gonna process this node by console logging. So this would be 1, right? And then we look at, so cross this out, then we look at which node?
Right.
The right node, right? Is there anything in the right? No. So then we go back up. So then where do we look at next?
The node.
The node, right? So what's the node?
2.
2, right? So we process this by console logging it. And then where do we look?
Right.
The right, cool. So then on this node, where do we look? Left, cool. And what's at the left?
Nothing.
Nothing, awesome. So then we look at what? The node, right?
Yep.
So what's at the node?
Tray.
3, awesome. Then we look where?
Right.
The right. Is there anything here? No, okay, cool. So we're done, right? And notice that in a binary search tree, the numbers are in order, right? So if we add a ton of nodes, it's always gonna be in order in a binary search tree. So now we're gonna do in order, pre-order. Let's do different numbers. 3, 1, 4. So pre-order is, what was it? Node. Yeah, node left, right. So we look at the node, right? So what's at the node?
3.
3, awesome. We're done with this, then we look where?
Left.
Left. All right, so where do we look at first?
The node.
So what's at the node?
1.
Cool, awesome.
Nothing left.
And then left, nothing, right, nothing. We go back up the tree. So then, where do we look now?
To the right.
To the, yes, the right. Yeah, so we're right here, right?
Mhm.
Where do we look at? No, awesome.
4.
Then we look at where?
Left.
Left.
And then we look at,
Right.
and then we're done. All right, next is post order. So post order, 7 is right node left. All right, so where do we look at first?
8.
Okay, cool. So you know the usual drill. It's gonna be 8.
So you did left and then right on 8. You should have done right and then
Yeah. All right. So then we're back up here. Then we look at where? a node, right? So what's the node?
7.
7. Awesome. Then we look where?
Left.
Left. Okay. Then we look at right. So what's at right?
Nothing.
What's
3.
that? 3. Awesome. And then we do
Left.
Left.
And we're
that.
done.
And then we're done.
Hooray!
So that's a common interview question. They're gonna say, "Oh, can you organize these nodes in a binary search tree? Can you like console log all of them in a numerical order?" And then you're like, "Oh, it should click that it's an in order traversal."
When you say console log, is there a function we could do to make that, or do we
Depends
just
on
wait?
the language. If you're doing C#, it's.
So yeah, you would console log it. Sometimes they want to output it as they want it as an array. So you would have to have a global variable that's an array. Push it into the array, and then console log it. So. Cool. All right. Okay, graphs. So now we're gonna get into graphs. So when you think of a graph, what do you think?
Google Maps.
So Joaquin,
Really?
so when you think of a graph, what do you think?
Set of coordinate points?
A set of coordinate points. Yeah, that's what I thought when I was learning graphs. But in a way, it is a set of coordinate points. And this, in the programming context, it's a set of nodes. So graphs are a collection of nodes, sometimes called vertices, with edges between some of them. So you can have nodes that are not connected to other nodes. You can have them like out in space. And then you have some that are connected to other ones. All right, graphs can be directed or undirected. So you could have two nodes connect to each other. There's no direction, they're just connected to each other. Or you could have where one node is connected to another node, and it's just a one-way street. You could think of it as one-way street. So graphs can have cycles. So you know the example I drew earlier with the tree, how it's cyclical? You can't have that in a tree, but you could have them in a graph. So trees, remember trees? We talked a lot about them a couple minutes ago. They're a specialized form of graph because they are a set of nodes. And they're just special because of how they have a root node. They have specialized properties that make them different from the typical graph. Okay, cool. So there's two main ways to represent a graph, an adjacency matrix. Oh wait, I want to show you guys different graphs. So let's start with a simple node. So is this a graph?
So there's a collection of nodes.
Yeah. It's a collection of nodes, but it could be one in a collection.
Oh, that's true.
Cool. Good. Good observation. So, is this a graph?
By itself?
Oh, by itself or with both of them together?
Yes. Yes, it is.
Yeah, that's a graph. All right. So, is this a graph?
Yep.
Cool. Is this a graph?
Yes.
Cool. Hey. I need to talk to you later. All right. Is this a graph?
Yep.
Yeah. Does everyone agree? All right. Cool. Is this a graph?
Yep.
Yes.
All right. Cool. Yeah. Pretty much anything's a graph. Good. You guys are very smart. All right. So, there are two ways to represent a graph: an adjacency list and an adjacency matrix. In the context of interviews, you're gonna see a lot of adjacency lists rather than an adjacency matrix. So, an adjacency matrix, is everyone familiar with Algebra 2 and how we had to do matrices and all that stuff? Cool. So then, an adjacency matrix is where you have, let's do like 2, 3, where you have your list of nodes on one side, or on both. Cool, and you state what's connected to what. So if you have a node that has 0, what's it connected to? It's connected to a 2, right? And you have 1, it's connected to what? 3. So we have a 1 node, it's connected to a 3. And then you have a 2 node, it's connected to what?
0 and a 3.
0 and a 3.
Oh yeah.
And then you have a 3 node, it's connected to a 1. Cool.
Cool.
So when you build your graph, when you have your set of nodes, you guys are all familiar with arrays, right? So then I remember a nested array can represent an adjacency matrix. And then we have our adjacency list. So our adjacency list works in a similar fashion, but it's more like an object. So you have your list of nodes, let's say 0, 1, 2, 3, and then you write out the nodes that that key is connected to. So for example, this could be connected to 1, 2, this could be connected to nothing, this could be connected to 3, this could be connected to, let's say, 2. And then you would write out the nodes and connect them. So this is useful. Notice that it's more like an object, and adjacency is adjacency matrix is more like a nested array. Okay, so now we're going to talk about depth first search and breadth first search. So in the depth first search, you go deep, whereas in a breadth first search, we go wide. So in depth first search is very similar to how we did tree transversals, where we go down and then and then we process each node. But with breadth first search, we go more across, and that's how we process each node. So with the depth first search, so we have, let's say, something like this. We would start here, process this. By process, like for example, you could just do a console log. This, then this, then this, and then it will go to the right. And then it'll go down. Okay, when it's done processing this, then we'll process the next one. But if we do breadth first search, it would start right here. Then we'll go to this node, this node, this node, then this node. So we'll go more left to right, or you could go right to left. Most cases, you'll see it go from left to right. Okay. So, since we're doing trees, let's make our own tree. All right. So a tree has what? Like as its smallest molecule. Like it has a node, right? So then what would the properties of that tree? Let's make it specifically for binary search trees, right? So a binary search tree, a node has a left and a right, right? Well, on the left side, it's smaller, right? And on the right side is greater. So if we do some pseudocode. So we have a binary search tree node. Can you guys see that? No, that looks bigger.
Yes.
Okay. So a node would have a value, right? And then we'll also have a left and a right. Correct?
See,
All right. So what would a binary search tree, the tree itself, what would it have?
just have the node. What do you mean? That's the root.
As the root, correct. And then that root would be of type, or BST node.
Beast
So
node.
for the sake of simplicity, let's make the value a numerical value. And on the left side, what's the type? By type, I mean, is it string? Is it
No, it's
another
beast
an
node.
object?
Beast node.
It's a beast node.
Yes, it is of type BST node.
So does anyone have any questions about that? So then, David in the back, this David, why would it be a BST node? I know I'm going kind of fast. It's because I want to cover a lot in a short amount of time. I'm calling you up. Okay,
Is it because it's basically another root?
it's another, you can think of it as another root. So remember that, throw it up here. So we said a root is a binary search tree node. So let's just concentrate on the node, right? So a node has a value, right? And that value is going to be a number. So for example, like,
1.
Kelly, what number do you want? 2, all right.
That's me.
And then a binary search tree node is going to connect to 2, right? To 2 values at most. So we're going to have a left and a right. So these don't have to connect. So in that case, it will be null.
Okay.
But that's by default. But if we're building it out and we're anticipating a node, this would have to be it's going to be connected to another node with its own value
And it's on left, right?
and its own left and right. Is that more clear? Yeah.
So
Question?
like left and right, is it a BST node because it's like a pointer to like another?
Yes, it's a pointer to the left is going to be a pointer to the left node, and the right is going to the right property is going to be a pointer to the right node.
And because what it's pointing to also has to have a value, a left, and a right, that's why the type is BST node.
Okay, cool. So we created our node, and now we create our tree. So our tree is going to consist of a collection of nodes. So you could think of this as the tree, and all these as nodes. So this would be a node, this would be a node, this would be a node. This is the tree, and this is going to be the root node. Okay, cool. So then we have our node, and then we have a tree. All right. So if we're gonna build a binary search tree, let's use JavaScript. Are you all familiar with classes in JavaScript?
Yes.
So we're gonna build it out using JavaScript. So, okay. Is this syntax familiar with all you guys for the most part? Yeah. Cool. So let's say we want to create a tree, right? So how would I create a tree? How would I reference a tree? I would let tree equals, or node, whoops. I mean node. Let node equals new BST.
And wouldn't you want to do let root equals new whatever?
Well, we haven't assigned it to a tree yet. So right now it's just a node. It's just a node. Once it gets assigned to a tree, then it becomes a root. So right now the focus is just the node, right? And we want to pass in a value of 4, right? Okay, is this syntax familiar with everyone?
Yes.
All right, cool. So then using ES6. Okay, so this means if no value is given, then the value is null by default. Okay, cool. Okay, so this dot value. What would this dot value equal?
Value.
Value?
Yes. Is everyone familiar with that? I know I'm going kind of deep.
Yep.
But when you're in interview setting, they're gonna tell you build a tree, and you're gonna be like, what? So you're gonna have to be familiar with all this. It happened to me, so learn from my experience. All right. So then we need a left and a right, correct?
Right.
So then, what would I write here? So what's the default?
Left is, what?
I don't know, it is in JavaScript.
No.
Yep. So by default, it's null. Because it hasn't been, this is just a floating node in space.
It hasn't
It
been
hasn't
assigned.
been assigned
It hasn't
a
been
node to
pointed
connect
to.
it. It's not pointing to a node. Yeah, that's the correct term. So this is our node. Cool. Any questions on just creating a node? A basic object, a basic node data structure. Cool. All right. So now we're gonna create a tree. So looking at our pseudocode, what do we need? We just need a root, right?
Right.
We just need to point to a root. Let me make this more clear. So the tree actually points, where did I put my marker? Oh, there. Okay, the tree actually points to the root node. And then this root node points to another node, and those nodes point to other nodes. Okay, so now we're gonna create a tree. So it's gonna be a class, EST tree, constructor. Is everyone familiar with what the constructor does?
Yes.
Yes, any questions? I see some stickers. Alright. I'm going kind of deep. I just want to prepare you guys for interviews. All right, cool. So if we wanted a tree, okay, this is how we would declare it, and we would pass in a node, right? So what does a tree have?
A root.
A root, right? Oops.
And that's gonna equal the node that you passed in.
Yeah. So then there's different ways of creating trees. Some people like putting in a value, and then it detects if there's a value, it creates the node right here. But yeah, so then, okay, so by default, node's gonna be null. And then we point to the node. Any questions about that? Another option is we could pass in a value, and then we could do this dot root equals new est node. Instead of node, it's going to be value.
Does JavaScript support to where you could have multiple constructors based on the signature? So could you have another constructor with node in it as a value, and if the various constructor gets called based on what gets passed in? You can't do that because you don't have types, right?
Yeah, I've never seen it done. I've never seen multiple constructors. I mean, if that was the scenario, I would just put it use
Well,
a
I
method.
mean, the idea is that if you could do that, which I think you're right, I don't think because you don't have types you can't do that, but the idea is that you have two constructors, one that takes in a BST node and the other one that takes in a value. If you pass in a BST node, the second constructor gets called. If you pass in a number, the first constructor gets called.
If that was the scenario, I would use a method where it detects if it's a
Yeah.
value or a node. So any questions about this? Cool. I think I'll end here for the talk. All right. Did you guys have any final questions? No. So I'm gonna give you actually a question I had on an interview and see if you guys can take it home, figure it out. Yeah, do what you want with it. All right. So I had a question where they asked me. They gave me a tree. So this isn't a binary search tree. This is just a tree, just a regular tree. And let's say this is A, B, C, D, E, F, G. And they told me, Felipe, these nodes represent who would be next in line for the throne. So this person will be next in line for the throne. Then it will be this person B, then C, then D, then E, then F, then G. Put these values in an array from in order of what's it called, inheritance or whatever. So then, what would you use in this case?
Magic.
Oh, what?
Patriarchy.
What kind of traversal? I'll narrow it
It
down.
was the line.
Okay, so what's
I
that
don't
called?
remember what you called it.
I think I heard it. So we start right here,
The one line.
then we go like this, right? So what's that called? I hope you guys are paying attention.
I wasn't.
Yeah, breadth traversal, right?
Yeah, breadth first traversal, right? And then they told me, okay, so the inherit, I got that part, and then they told me to go, okay, it goes, they want the inheritance to go like this. They switch it up, and it's like, oh, that's the other one, the depth first traversal. So, you guys, that's an interview question. So try writing an algorithm. Now that you know what kind of traversal it is, try writing an algorithm that does both cases. So that's my homework for you guys. Oh, and then before that, they tell you build a tree with those nodes.
Yeah.
So try doing that. Okay, cool. So we have Mauricio, right? The new guy. So
New guy.
this talk is over. Feel free to, everyone, crowd around him, make him feel welcome. Where are you coming from?
Or scare him, you know.
Where are you coming from?
Where do I live?
Yeah, where are you like driving from?
Oh, I live down here in Fontana.
Fontana?
Yeah.
Hey, Fontana. Cool. All right. Thank you guys.
Thank you.